welcome everybody. We've had nearly 300 people register for this webinar, so I think a lot of them are waiting to get the recording, but we'll go ahead and go live. Now, if anyone's got any questions, you can go ahead and there's a little Q&A form you can go ahead and fill out to submit a question. I will try to address those at the end once I get done through our content here. So this should take about an hour for us to do. So today's webinar is all about building real-time streaming web UIs with Blazor and Akka.net. This title actually kind of undersells what we're really doing today, which is that we're actually talking about how to build like multiplayer Blazor applications using Akka.net as basically the synchronization layer behind the scenes. So we're going to take a look at two little applications. One of them is going to be a kind of a private beta of a product that we've been developing internally here at Petabridge. The other is actually the more interesting and more complicated of the two of them is actually a public open source code sample that I've been developing for over the past couple of weeks. So a little bit about me. So my name is Aaron Stannard. I'm the founder and CEO here at Petabridge, also one of the original creators of Akka.net. I've been supporting the Akka.net project in some way, shape, or form for 10 years, actually a little bit over 10 years now. I've done a lot of work with customers and a lot of different spaces with it. So everything from SaaS to payments to IoT to energy to healthcare, you name it. I've seen and done kind of a lot over a lot of industries over the course of my journey with Akka.net. What we're going to dive into today is something that is kind of a new territory, I would wager, for most people who are attending, which is learning about doing not just, let's say, streaming UIs on the real-time web, but actually being able to do like two-way interactivity via the real-time web. Now, it's been technically possible to do this. The primary trailblazers around it have probably been people building browser-based games. They've probably been the leaders in it. But other folks who've worked on building browser-based social applications like Discord, the browser-hosted version of Slack, they've also had to deal with these types of issues as well, which is learning how to leverage both WebSockets and, let's say, a big distributed system like Akka.net in order to build scalable, real-world streaming UIs, or really streaming applications using Akka.net actors and all these other real-time web technologies to power everything behind the scenes. So we're going to go ahead and cover a number of different facets here. The first thing we're going to start with is thinking about if you're going to build a real-time UI, your choice of interactivity model is probably the most important decision you have to make. Everything after that kind of follows a natural set of, let's say, consequences. So we'll talk about choosing your interactivity model. I've got examples of both types. There's only two types of interactivity models. One-way interactivity, a real-time dashboard, is going to be the example we use here. The more fun interactivity type is two-way interactivity, where users can influence each other while they're using your application, or users can influence other things like devices on the network. So we're going to talk a little bit about both of these interactivity models. Next, we're going to get into some of the guts of working with Blazor itself. Now, if you have never looked at Blazor before, we should give you just enough information to kind of wet your beak with it a little bit as part of today's course. We're not doing anything super sophisticated from a Blazor UI standpoint. We're basically using Blazor server behind the scenes to do all the live rendering. That's going to be what powers the WebSockets and update loops for us. So we're going to be taking advantage of that behind the scenes. And we'll be using some third-party components like Mud Blazor to do a couple of things here and there, but we're keeping it pretty vanilla as far as Blazor goes. The really interesting question when you're starting to work with real-time web is who owns the truth in the system? So we're going to talk a little bit about the difference between local and global state in a real-time application. So for instance, the state the user has on their screen versus the state that's on the server living inside, let's say, like a cluster sharded actor somewhere. Those two values should ultimately synchronize over a period of time. Eventual consistency is kind of the name of the game here, but we're going to talk about some practical considerations for doing that. Then finally, we're going to talk a little bit about using Akka streams to handle some practical issues about client and server sync. A good example of this is anyone who's done WPF work before, or maybe you've done some mobile work, you've probably had to deal with things like click and mouse debouncing before. That same issue is going to show up inside this application since the multiplayer MS Paint uses a lot of mouse movement to go ahead and do drawing. We need to implement a minor form of mouse debouncing on there in order to reduce the amount of strain on our network by like an order of magnitude or two. So that's one of the things we're going to use Akka Streams for. We're also going to use Akka Streams for just generally speaking, dealing with the update loop for how we render updates on the UI side. So that's going to be another thing that we touch on. And then finally, we're going to talk about some subtle issues to bear in mind. Things that will not, in a little toy example, where I'm just running, let's say, a Blazor inside a single process, these are issues that would probably never come up. But in a big distributed system where you're trying to do things like a live deployment and you want to make sure users can continue using your app while you're cycling out backend nodes, there's actually some subtle problems that we've addressed in our drawtogether.net code sample that manage some of those problems. Now, we don't do everything 100% of the way through that you would really want for a production grade application. I'll cover some of what those to-do items are when we get to that section, but this is important. This is the information you want to have if you're considering building an application like this and you want to productionize it. So that's what we're going to get into today. So let's go ahead and start by talking about traditional web UIs. HTTP 1 and HTTP 2 are largely built around request response oriented communication, client pull or client pull models. That's really kind of the name of the game here. And this is because HTTP is generally speaking a stateless protocol. Now, HTTP 3 does introduce some streaming capabilities now. I'm not sure, I've not tried to program against it directly, but does introduce some streaming capabilities, but by and large, I'm guessing that that's mostly stuff that browsers are going to take advantage of. You as the end user, or you as, let's say, a web developer, are probably still going to be working with good old-fashioned HTTP request response, even when that comes out. Now, traditional web UIs have been getting, I hesitate to say this because there's some things that kind of complicate it, but generally they've stayed more or less the same and are relatively simple, unless you start going down the crazy, JavaScript ecosystem stuff for doing isomorphic React UIs where you have 1,000 NPM packages for doing left pad and all that stuff. I say it's simple, but that obviously comes with some caveats. My objection would actually be that most traditional web UIs have gotten intensely complicated over the past several years. One of the things that we're going to try to accomplish with Blazor, and why we're doing this talk on Blazor and not SignalR and JavaScript, is that real-time UIs allow us to go ahead and do streaming over a persistent connection. That's what SignalR is ultimately going to be used for under the covers, is this persistent connection piece. And they allow us to do both client and server push, where it's a duplex connection. Clients can send events and can receive them in real time. This is used to power lots of real-time applications such as webmail clients, Twitter, Discord, Slack, you name it. Even things like multiplayer video games. The big difference between, let's say, a real-time UI and your traditional web UI is that real-time UIs have to really have to be stateful in order to actually function properly. If you're trying to go ahead and do, let's say, stateless CRUD, but over a WebSocket, that's going to end in tears, and you're probably not leveraging WebSockets correctly if you're doing that. So generally, there needs to be some state somewhere inside your system. Actors are a very good place to stick them. And the name of the game behind real-time UIs is very low latency. You cannot have a real-time UI that has huge amounts of lag associated with it. So in essence, we're building a soft real-time application where the software doesn't fail if we fail to, let's say, get an update delivered within a short window of time, but the user experience degrades significantly. Imagine building, let's say, a Discord-like application where it took 5 seconds between when you sent a message and I saw it. That would not be a super, useful application. That would be pretty bad. So service level basically correlates with low latency in here. The quality of service correlates with low latency. Finally, real-time applications, in order to achieve low latency, the reason why we're stateful is so we can be reactive. We can react to inputs in a very short period of time and make sure that our outputs are transmitted directly to each relevant client with as little latency as possible. So the reactive programming model suits this quite nicely. So that's what we're going to try to accomplish using actors. Now, from a connectivity model standpoint, there's two ways of thinking about real-time web UIs. One-way interactivity is by far and away the simpler of the two. And this is where the server is doing all the pushing. The server receives events from someplace else. So for instance, maybe it's receiving events from OpenTelemetry or some other type of monitoring system you put in place. Maybe it's, I don't know, tailing events that are being written to an event journal or whatever. And it's going to render those events it's receiving as some sort of structured data that it can send back to the client. So a live dashboard. So for instance, if you work in finance, you might have a live dashboard showing ticker updates for various equities or currency pairs or whatever it is you're trading on inside that system. Or maybe you're doing, let's say, monitoring of things like servers or hardware out in the field. Live dashboards would be really useful for that. Other examples of this type of one-way interactivity model include things like streaming services. When you're watching Netflix, the only data that you're really kind of pushing back to it when you're receiving it is basically maybe the current watch position of that video. So you can pick up where you left off if you have to pause and come back or reconnect to it on another device later. There's not a huge amount of interactivity from the clients here. Push notifications are another example where you're receiving, let's say, a real-time stream of updates from something like Twitter. And every time you go and actually, author a tweet or do a retweet or like something, you actually are submitting that over like a separate HTTP API. The push notifications are only used to let you know about new content being available in your feed or new notifications that affect you. So let's take a look at a real simple example of a real-time dashboard real quickly. Let me grab this. We started working on this last summer. So these days, I guess you'd call this Aspire for Aquanaut Cluster. It's basically what this is. But this is a product we've called Aquanaut Ops Center. And this is a super UI-driven application. So the way my team and I have been building it, whoops, I think I just closed my browser tab here. Here we go. The way my team and I built it is normally we do bottom-up development where we start from the bottom of the source code and work our way to the front. For things that are super visual, like live dashboards, we strongly prefer to do things top-down. Design the UI first, work our way down towards the implementation details. So this is kind of our UI prototype we've been using to try to get our data model figured out. And hey, look at this. You can see one of my alert rules just kicked off. That's what this little flag is here. You can see some live events coming in. If I delve into one of the environments, you can go ahead and see the amount of uptime is going up. We can see memory and CPU usage are staying relatively stable. Oh, we've had another node join the cluster. I can take a look and see the total number of shards and entities. I'm starting to get a whole bunch of alerts now. This data is all simulated, by the way. We created an Aquanaut cluster simulator so we could just do UI prototyping. But in a real production system, we would be connected to an actual, let's say, gRPC endpoint that's exposed to us via one or more nodes inside an Aquanaut cluster. And that's where we would be sourcing these events from inside of here. So we're not going to dive into a huge amount of this code because the next sample we're going to look at leverages the exact same design technique this does, but it's even more interesting because it's a two-way interactivity system where events are both being pushed to the client and the client is also pushing events to the server, and those events have to get propagated to other clients, which makes it kind of a more sophisticated and fun example to work with. But I just kind of wanted to show an example of what's possible. By the way, this is using Aquanaut streams to do all these live updates on here. So let me shut this sample down real quick. And we will eventually ship that product. We just kind of put it on hold for other things for the time being. Two-way interactivity is much more complicated than one-way interactivity. And the reason being is that with one-way interactivity, synchronization is relatively simple. The server is the total source of truth, and it just has to distribute events out to all the clients and make sure each client fully processes each of them. That's a fairly straightforward endeavor. With two-way interactivity, both the client and the server have the ability to initiate the creation of new events. So that means that we have this two-way sync that has to be managed. The client's got to make sure the server gets its events. The server has to make sure it broadcasts those events to all the other clients. So the class of applications you can build using this interactivity model are, in my opinion, much more interesting, and also fun and also valuable than one-way interactivity. These include things like chat and social apps. Probably the most fun example of these is online games. You can go ahead and build multiplayer games using this technique with Blazor and have them all run in the browser out of the box. The other thing you can use this for is collaboration software. That's kind of the use case that we're falling into it today. One of the things that inspired me to build this sample was that actually one of our customers has had to build a large scale collaboration system on top of Akka.net for their software as a service product. And that inspired me to think, how could I try to take that same type of a style and have it run over Blazor instead? They're using traditional JavaScript and all that stuff to do it. I thought, we should try using this with, let's say, a more cutting edge .NET tech stack and see if it's actually in a lot of ways cheaper to deliver that experience than what they had to do. And so far the results are pretty good. So let's take a look at our sample here. Now you should get an email that has a link to this if you haven't gotten one already from your registration email, but you'll get one after the webinar is done. This is our public code sample right here, github.com/petabridge/drawtogether.net. So I've been developing this kind of out in the open. Let me shut that down. So this is drawtogether.net. It uses Blazor on .NET 8. It uses my ASP.NET identity. So we actually are using real identity and authorization under the covers to make sure that only authenticated users have the ability to draw. And what it basically is a multiplayer MS Paint session. So I have two different browser tabs open. Let me see if I can grab my second one, which I've got in an incognito window over here someplace. Let's see, where did I stick that? You know what I'm going to do? I'm just going to close PowerPoint for a second so I can see. There we go. All right, I'm going to bring this over. That's my little incognito window. And then I'm going to grab my main window right here. Okay. So if I go and reload my screen, I can see that there's a paint session with only one person in it right now. I can see this content here. And I can see that I'm logged in as Aaron at Aaron Standard here. I'm logged in as Aaron at Petabridge over here. So I've got two different real accounts I'm logged in as. And both can see this active paint session behind the scenes. And now we can see, by the way, that the number of users in this active paint session ticked down to 0. Oh, that's pretty cool. So we're able to keep track of users joining and leaving these sessions respectively. Well, I'm going to go ahead and rejoin this session here. You can see all my old content gets pulled up, and I'm going to rejoin this session here as well. You can see these GUIDs. These are, I need to really add usernames to make things a little bit more user friendly, but you can basically see these are the unique identities of both of these users. Now, I can go ahead and select a paint stroke here. Let me grab red. I'll make the cursor size nice and big, and I'll go ahead and draw that line right there. And over on the right, I've got blue. I'll go ahead and draw this, actually, whoops, draw blue, draw this line right here. And I can also clear the screen if I want, add some new lines there, add some new lines here. And if I leave this drawing session and this user continues to draw and I rejoin it, I don't miss any of the content that was there previously. Looks like I've got a little bug where my default cursor color gets reset to black each time I join. I'll have to fix that. But otherwise, looks like we've got collaborative drawing in place here. And I can also go and create another new paint session that is unshared. Let me go ahead and make some transparent, blow up the cursor size a bit. I can do some transparency here. I've got little gaps in my drawing here. I think this is a math error with how I'm doing drawing connected shapes, but that's all available here. Go and change the color a bit more, etc. So you get the idea. This is meant to be kind of like a multiplayer MS Paint. If both users go back to the home screen, we can see there's only one active user in each of these sessions. If I wait a couple of seconds, both sessions will tick down to having 0 active users. There we go. 0 active users in both sessions. Okay, so given that, let's go ahead and talk about how do we actually build something like this. So let me go ahead and jump back to our PowerPoint here. And the first thing we're going to dive into is talking a bit about the Blazor side of things. We're going to spend time covering all the Akka.net details as well. No problem there. But we want to introduce Blazor first. So the first thing we kind of want to think about if we're going to design a real-time UI with Blazor and Akka.net is who's responsible for doing what inside the system. Blazor owns the visual representation of content. You know, if you're looking at this as an end-tier application, Blazor owns the presentation layer. Blazor is also responsible for managing the render state on each page. So that canvas we're looking at earlier, that's actually an SVG. And every time I do a brushstroke, I'm basically drawing a new connected line SVG when that happens. So Blazor is responsible for taking all the little events that Akka.net's going to persist and transmit and rendering them into those strokes on screen. Blazor is also responsible for the transportation of all updates between the presentation layer and the server. This includes client to server and server to client. So this is going to happen using a piece of infrastructure that Blazor server has called the Blazor Hub. This is basically like a little implicit SignalR connection that's available behind the scenes. It will automatically serialize and deserialize all of the rendered updates for you without you needing to write any JavaScript code or anything else. That's one thing about the sample I should call out now. There's actually no custom JavaScript anywhere in here other than whatever mud Blazor adds to it, which we just have to rig up in our default template. I personally wrote no JavaScript to make any of this work. It is all C#. The other thing that Blazor is going to handle is dealing with authentication, and it's going to generate the drawing session IDs. This is basically just generating a GUID. That's pretty simple. Akka.net is going to be responsible for managing two things. We're going to be responsible for managing the local per server and per user subscription management. Subscriptions have to exist locally per server because that's where the WebSocket is. So that means that we need to keep track of who is connected on which instance inside the system. We use Akka.cluster sharding and a little pub sub system to make it pretty easy for a drawing that has users that are spread out over many servers that will all still work together transparently, just like you'd expect from Akka.remote. But we do have to bear in mind that WebSockets are local. Effectively what this is, if you're an experienced SignalR user, you've probably delved into the idea of like a SignalR backplane before. We kind of implicitly built one here, just using actor messaging is all that we're doing. So no need for Redis or any of that other stuff. The only infrastructure drawtogether.net requires is a SQL Server database for doing persistence. And then I guess I need an email provider. I think we're using Mailgun to send registration emails for confirming people's accounts. And that's it. No other infrastructure is needed. Akka.net's also going to take care of debouncing and batching updates. This is actually important from a networking standpoint. We're also going to be responsible for keeping track of the drawing state of each individual drawing session. So this is basically the idea of the source of truth belongs to an Akka.net entity actor. We're also going to be responsible for making sure that the state of each of the different drawings is persisted and reentrant. In the event that we do a live deployment in the middle of people drawing, we do not want to blow away everything that they've been working on, even though this is meant to be a simple toy application. This is a thing we need to be able to do for real if we want to learn how to build things like a multiplayer game using the system. Finally, Akka.net's also going to deal with serialization. We're not going to spend a huge amount of time covering this. We have a YouTube video on message and state evolution with Akka.persistence. We're using that technique, which is basically using protobuf under the covers for serialization. This only matters for Akka.persistence and Akka.remote. This doesn't affect the Blazor side of things at all. All right, so that's kind of the setup for what we're going to think about in terms of who's responsible for what. The first problem we kind of need to dive into is deciding how we want Blazor to run behind the scenes. One of the big things that changed a lot in .NET 8 is they've been trying to kind of unify. This is the whole Blazor United thing they're pitching. They've been trying to unify a whole bunch of the functionality in Blazor in .NET 8. The mode that I have found easiest to work with when we are trying to do these sort of real-time applications is Blazor Server Interactive mode. Now, this does have some scalability challenges and I say that just kind of in the abstract. In real terms, you're probably fine. But in the abstract, the server is going to be doing some rendering during each one of these. That's the sort of tax you pay for this mode. But it's by far the easiest to manage. And this is what's going to keep things like in pure C#. You could, in theory, have a separate SignalR powered server and have Blazor WebAssembly do all the rendering we're doing here. But you would need to ship basically two different apps. One would be a static web app front end, the other would be your Blazor backend. And you would probably have to do a little bit of JavaScript to make that completely work behind the scenes. I opted not to do that because I don't think this is a huge performance concern for us. And this makes it so I can ship everything as one application and not have to worry about it. So that's why I picked that. We're going to use the built-in Blazor hub. This basically automates away all the serialization, and there's no need to make any explicit calls to SignalR here. So it's one less thing we don't need to do. The other thing you could do, yeah, I mentioned this alternative. You can alternatively set this up with Blazor WebAssembly and a separate SignalR server. I've done that before. It's more work. But if you are really concerned about performance, and let's say if you were really trying to build, a high performance, high use multiplayer game, you should probably design it that way. But you could easily prototype it like this and refactor it into that later if you wanted to. All right, so we're going to start with the first problem you will run into with Blazor and .NET 8 if you want to use, let's say, Mud Blazor, or you want to use Blazor Server Interactive Mode, and you also want to use something like ASP.NET Identity. .NET 8 changed some of the default render modes in Blazor, and for reasons I still don't fully understand, ASP.NET Identity does not work with server-side rendering at all. It only works with WebAssembly. So one of the things you will need to do if you want to use Blazor server mode here is this is the workaround that Microsoft currently recommends. You basically need to set inside this is the app.razor file. This is kind of like the basically kind of sets the master layout and template for all of your Blazor pages in this application. One of the things you'll want to do is have a little parameter here that checks to see what page you're on. If you're in the account area, that's basically ASP.NET Identity right there. You're going to go ahead and want to set this back to the default render mode. Otherwise, everywhere else in your application, you should set this up to use interactive server. This caused me a lot of trouble when I was first trying to update this app from .NET 5 to .NET 8. So I wanted to make sure you didn't have to learn this the hard way. But anyway, that's kind of the first little pitfall you might run into if you want to use .NET Identity and Blazor. Now, moving on to the actual fun stuff inside this application. This is, I believe, from our drawing session page. Actually, no, this is from our home page right here. And I forgot to add an annotation in the bottom corner. This is how we're going to try to load the initial UI snapshot. In fact, if I go and pull up Writer here, this is going to be, if I pull up Draw Together and I go to, let's see, Components, and I go to Pages, and I go to Home, and I'll zoom in just a little bit. This is basically this page right here, our active paint sessions. We're going to go ahead and try to list all these paint sessions that all the users are participating in. Because if you want to draw together with someone else, you want to see where everyone else is, right? That's the first thing you're going to see when you log in. So what we're going to do is we are going to use the onInitialized method pretty often inside our Blazor application. The onInitialized method, if you're not familiar with Blazor, gets invoked basically after the page has started to render but hasn't quite finished yet. This is like a pretty good, it's kind of like if you're an .NET user, this is like the pre-start hook basically for this page. So what we're going to do in here is we are going to get a reference to the all drawings index actor. And this is using Akka.Hosting's IRequired actor right here. We're going to get a reference to this actor, and we're just going to use a simple request response operation. We're going to say, hey, I want you to give me a list of all the current drawings. And so we'll go ahead and get an initial snapshot this way. And we're going to populate this dictionary right here with those values. And then we're going to start a background data pump. This page, this initial UI snapshot, this homepage here, is basically one-way interactivity, although it can be influenced by people starting new paint sessions and joining them. But basically all the data comes from the server right here. So let's take a look at how we're actually doing this. Now, if you're not familiar with Blazor, at the very top of your Blazor page is what I've highlighted on screen right here. These are basically where you can specify your using directives. You can specify what interfaces this page should implement. And you can also specify dependency injection using the inject directive right here. So we're going to inject two things into this page. The first is we're going to use Akka.Hosting's DI system to inject the all drawings index actor. This actor has access to, we're basically using Akka.Distributed data behind the scenes here. So we're using CRDTs to move the set of all available drawings around inside the system. This actor is going to allow you to subscribe to those updates and receive them as an event stream. Then we're also going to inject the actor system right here. And I believe we do that in order to materialize Akka streams graphs for handling our subscriptions. Now, if I scroll down here, we just have some basic MUD Blazor components. I've created a MUD container. This is basically a layout element. And we have a MUD data grid. That's going to be what populates the set of all drawings people are actively working on at any given time. So this is basically kind of like a table, if you will. And what we're going to do is we're going to reference all this drawing activities, this dictionary right here. We're just going to say, get me all of the values from this dictionary. And for each one of those values, I would like you to go ahead and render a row that has these columns. So it's a little bit of data binding is what we're doing here. So this is our data. We have a dictionary that has the drawing session ID, and we have a little data structure here, this record, that basically just includes the number of active users, the last update, and then has a flag to indicate whether or not this drawing session has expired. That's going to happen if the drawing session has had no users in it for, I think, 15 minutes. We automatically evict that drawing from the system and delete its data. That's just to kind of help basically make sure we remove unused assets from the system after a while. So we have our little data pump right here. We just do a little request response. We send the all drawings actor this get all active drawing sessions request, and we get a read-only collection of drawing activity updates afterwards that we populate into this dictionary. And then from that point onward, here's where the streaming stuff kicks in. From that point onward, we're going to go ahead and call this run subscription method right here. So architecturally, whether you want to build a one-way interactivity system or a two-way interactivity system with Blazor, one of the things you're going to want to do in order to power the live updates that you're receiving from the server is kick off a background task that's going to continue running as long as you're on the page. That's what this method does right here. It's an async task that basically we don't bother awaiting on. If we awaited on this, the page would never finish rendering. So that'd be a problem. So instead, you want to kick it off as a detached task, which is what I'm doing here. At the start of this task, we are going to create a source.actorref. So this is Akka Streams. This actorref is going to be able to receive a list of drawing activity updates. And we're going to go ahead and call pre-materialize here. This will give me a source actor to work with, and this will give me an Akka Stream source. I'm going to tell the all drawings actor, I would like you to subscribe this source actor, this iActorref, to updates. And what's going to end up happening is I'm going to take my Akka Stream source and I'm going to call run as async enumerable. And I'm going to pass in the actor system right here. That is going to cause this actor to basically create an internal system.threading.channel, more or less. And we're going to asynchronously enumerate on its results here. And we're going to pass in a cancellation token as well. I'm going to talk a little bit about that in more detail in just a moment. But this async enumerable, every time the server has an update for us, it will push it to all these subscribers. In fact, let me go to this actor real quick. Let's see, this actor is the all drawings index actor. This actor is dead simple. It's basically has this last right wins dictionary. This is our CRDT. We're going to do some stuff with distributed data. We're not going to spend a huge amount of time talking about that. But we have a hash set of subscribers. And this actor, by the way, runs as a cluster singleton. So what's happening inside the system here. So there's only one of these throughout the entire system. Every user subscribes to it. Every time we get a update to our distributed data feed here, we're going to go and merge that data into our local copy. And then on a periodic timer that we're going to run here, we're just going to iterate over all these subscribers and basically give them the most recent updates. And this set of updates is bounded to something like, I don't know, 50 maximum updates here. We're just going to deliver that as a list back to all the subscribers. Every time we do this .tell operation right here, that is going to cause this async enumerable to tick once. And that update is going to include several different items that can be rendered in here. Now, what I'm about to show you next is actually pretty important for making sure your render performance is good in Blazor. We're performing a little bit of server-side debouncing here. Rather than pushing, let's say, 30 individual updates over the network, which each one would need to be serialized, and then each one would cause this await to go ahead and tick, we're actually transmitting those updates in a group together. And one single list object is getting transmitted. And then after, so that means I only have to have one await and one network message to process that update. And these messages are very small in terms of how big they are. I am going to iterate over each of those items in that list, and I'm going to modify some of the content in my dictionary. And then at the very end, after I'm done processing that batch, I invoke this built-in Blazor method, state has changed. This is going to trigger the SignalR flush and the re-rendering of our UI with all this new content here. So this allows me to debounce the rendering side of things and to debounce the network transmission here. This is going to result in the same type of data all changing, but it's going to happen in fewer trips with fewer updates, both between the server and the client and between the Blazor hub and the actual UI element as well. So this is going to help keep things reasonably efficient for powering, let's say, lots of updates all at once. We will also use this technique on the next page we're going to take a look at, which is the actual painting page as well. So that's kind of the first key piece of advice on working with Blazor here. Now, next, I guess I already kind of covered all this. Yeah, did all that. Now, one important piece of advice that you've seen me do already on the home page, and you're going to see me do this on the actual paint.razor page. This is where we're doing all the brush strokes and everything, is you're going to want to make sure all of your pages that are doing real-time streaming implement the iAsync disposable interface. The reason for this, and you just do that declaration right here, the reason why we do this is that if the user navigates away from a page, this interface will get invoked and it will cause us to go ahead and dispose the elements that are powering the real-time updates behind the scenes there. This means that if we're materializing actors, or if we are, let's say, running iAsync enumerables, or if we're doing whatever, we can do things like invoke that cancellation token, or we can tell the server that a user has left this paint session. This will help us make sure we don't accidentally leak resources inside this application. You don't want to have a whole bunch of actors streaming data to users who are not there. So this will help us make sure we get that cleaned up. It'll also help us make sure that if we need to do something on the visual side of things when a user leaves the page, such as tick down the number of active users in the session or decrement the number of people who are, let's say, visibly working on this document in the index, this event handler will allow us to do that. So this is a good practice that we want to make sure we implement everywhere we're doing background streaming. So if we go back to the home page that we were initially looking at, I have my dispose async method here, and the primary thing that I'm doing is I'm canceling this iAsync enumerable, which should also cause this source actor to go ahead and terminate when this happens. And in fact, if I want to be, oh, here we go, this is clever. So once this iAsync enumerable exits, I actually explicitly send a poison pill to that actor to make sure it shuts down. That way we free up resources. One of the things we want to be mindful of, and we'll touch on this in the final section today, one of the things we want to be mindful of if we're doing all this background streaming is this creates asynchronous resources that are not specifically tied to the life cycle of the page the user's on. By implementing iAsync disposable and guaranteeing those resources get terminated, we do tie them together. So that way, whatever the user's, let's say, navigation state is, we can make sure that's getting reflected on the server they're connected to, and we're disposing all the resources we need to. So iAsync disposable will help us do that. Good practice to get into, make sure you do it. Now, the next thing we're gonna dive into a little bit is dealing with local versus global state. So most of what we looked at so far has been the local state. Things like the dictionary. I'll go ahead and pull up my Blazor document again here. This dictionary of all the active drawing sessions and how many people are currently in it, this is an example of local state. This state is specific to a single user's browsing session on this page right now. If I have several tabs open looking at the same page, I might have separate instances of each of them on here. So this is local state. It's localized to like an active tab is kind of the way I'd mentally think about it. We also have some actors running on the server that are localized to a specific user's session, where that user has a SignalR connection to this server, and we are managing the sync state for that. And then finally, we have global state. What is the true source of truth for all users actively accessing a given document on here? So why actors for state? Well, since most of the people attending joined here from the Pettibridge mailing list, I assume many of these points are already clear to you, but just for the sake of being thorough, I'm going to go through them. Why do we want actors for state? Well, the ability to accumulate state in memory and react changes to them in real time is the primary driver of low latency in the system. The fact that we're not round tripping to the database every time someone wants to do something is very powerful and allows us to keep things snappy inside the system. Most of the updates that we're doing can be sub-microsecond if we're running locally. If we're sending data over the network, that latency will be higher on the order of, let's say, like 1 to 3 milliseconds typically. But we're still talking like faster than the human eye can visualize things. So latency should be so low that it's not even noticeable if we're doing everything right. The other reason why we want to use actors is it's basically allows us to reduce big problems into small, easily understandable units. We're going to take a look at the drawing session state actor in just a second, and you'll see what I mean when we dive into that. The fact that we can run many of these actors concurrently helps us guarantee that all the updates happening to all these drawing sessions is always thread safe. So by virtue of the fact that actors process messages one at a time, this actually solves some of the really obnoxious synchronization problems you would have if you tried to build this application without actors. So if you were trying to use, I don't know, semaphores and locks and stuff like that to try to do it, good luck. That wouldn't work unless you had a distributed lock. And if you did, that would make the amount of latency and the amount of processing power you need to actually deliver this application go up significantly. Actors help keep things safe, understandable, and fast. The other thing that actors do is they simplify a lot of the programming. The fact that the actor that owns the session state could be local or it could be remote on a separate process is kind of immaterial to us. Our programming model is designed to just work with the actor reference regardless of where it is. The serialization layer will take care of any of the messages that have to span the network. And finally, the system is really scalable. We have a bunch of different actors we create in order to manage all the different little pieces of subscription state that have to happen for each user, in each drawing session, et cetera. They're cheap resources. These actors use less than a kilobit of memory usually. So we're not super worried about them. We can run millions of them in a single process and be fine. Lastly, actors are fault tolerant. If there's going to be, actually, no, there's one more point after this. They're also reentrant. There we go. They're fault tolerant. Crashes only affect the actor that threw them. So if one drawing session gets into a corrupted state, that drawing session erroring out is going to have zero impact on any of the others. And finally, actors are reentrant. I can reboot that failed drawing session, and the only consequence might be that one brush stroke never got saved, which is okay, not going to hurt us. So we'll go ahead and talk a bit about, skip through some of this here. Actors make concurrency easy. This is because we process messages one at a time. So as a result of this, when users are making their different brush strokes inside drawtogether.net, we're serializing those messages. And I'm using the word serialize a little differently here. I mean that we're serializing the order in which those strokes get rendered on screen. The fact that actors process messages one at a time, it makes it easy to reason about that. If you didn't have an actor for that purpose, you would need some other sort of distributed queuing technology for that probably. If you're talking about going over the network, which we are in this case. So actors make concurrency easy without needing any additional infrastructure. Finally, they're going to allow us to reduce all of the different volumes of data that have to go into managing each of these different painting sessions that are running concurrently. This allows us to make sure that each painting session gets encapsulated inside its own actor and gets updated independently and concurrently from all the rest of them. Now, why Akka.NET for this? Again, I made this presentation originally for folks who weren't that familiar with Akka.NET. But the gist of it is that Akka.NET Core makes it really easy for us to run actors locally in the process where our Blazor server is located. Akka hosting allows us to tie in with things like the dependency injection system. You've already seen us leverage that with the inject directive on our Blazor pages. And finally, Akka.cluster and cluster sharding and Akka.persistence. They solve the most difficult problem that we're addressing here, which is making sure that we can spread our actors out across multiple processes, redistribute them in the event that we're doing things like a deployment, which causes us to bring some nodes down and spin new nodes up. And it guarantees that all the data is highly available and consistent, and also reentrant. So cluster sharding plus Akka.persistence really kind of gives us all of the consistency and availability we need to make this system production worthy. If we didn't have those facets, then this process could only really run as like a single instance. And if anything went wrong with it, everyone would lose all their data. But since we want to try to productionize it like how you would with a real customer facing application, we're using the proper tools for doing that. And then Akka Streams is probably the most important ingredient for the actual smoothness of the user experience. This is going to take care of all the problems dealing with rates and volumes. Specifically, it's going to allow us to debounce events going from the client to the server and vice versa. It also, most importantly, allows us to materialize the stream of data coming back from Akka.NET as an async enumerable. Now, on Blazor server, I can do things like ask an actor a message and get a response back and have it rendered on screen. That's no problem. But trying to go ahead and update UI elements directly on a Blazor stream, by far the best way to do that is an async enumerable. That's all natively supported with the Blazor hub. And this is going to result in basically server push events when this happens. So that in combination with that render state changed method you saw me invoking, that's going to be kind of the key ingredient for being able to deliver a real live update to a user looking at your Blazor page in real time. So let's kind of think a bit about our state model to some extent. Now, normally when we're talking about real-time web UIs, everyone wants to get excited about the cool UI elements because that's what's fun and everyone can kind of interact with them. But the real key to making this system work well is actually having a solid state model for being able to think through who is responsible for what inside this system. So the first thing we're going to do is, and we're going to scope this to a single drawing session, one paint session that might have multiple users spread out across multiple servers on it. We're going to have a draw session entity actor. This is our cluster sharded actor. There's one of these per paint session globally throughout our entire system. So we're going to have a single draw session entity actor deciding who sees what. Now, in theory, we could do local versions of this actor on each server and have them use Akka distributed data to do that if we wanted to. That's totally workable, but that's just a little bit harder to persist and probably not as user-friendly as cluster sharding is. So that's why we went with that design choice here. Now, the next thing we got to do is on each individual server, we have to manage all the different users concurrently trying to push events for a specific paint session on it. So if I have, let's say, 10 people in a paint session spread out across 3 servers, I'm going to have a local draw session actor that has 3 users here, 3 users here, and I guess 2 or 4 users here, depending on what number of users you want to have. And all of the different updates that are going to go out to each of those users are all going to be run through this local draw session actor right here. This actor has to have local affinity with the SignalR hub responsible for pushing updates to that user. This is kind of where our backplane functionality for SignalR enters the picture here. Any updates to the global state are going to get pushed to these local draw session actors. And these draw session actors are going to push those events into the Akka streams by endpoints for each of these individual users. And this will cause everyone's screen to go ahead and get updated. Now, if you're working with raw SignalR, in theory, you could use a SignalR group and eliminate the need for all these individual participant stream actors here. But since we're kind of just using the Blazor hub and we're not touching SignalR directly, this is how I decided to do it. And it ended up being pretty easy and a lot less code. So that's why I did it this way. But this is our hierarchy for how we're going to synchronize state inside the system. So just to kind of take a look at what the application looks like from an infrastructure standpoint. Now, I haven't had a chance to finish doing this part on the code sample, but I'm planning on using .NET Aspire to go ahead and deploy this to Azure App Service using basically Akka.management to go ahead and form a little cluster. And what we have here is we have our Blazor hub plus UI. That's where all of our local actors live. And then we're going to spread out a shard region that has all these source of truth actors for the paint sessions. So everyone's kind of part of a cluster here, but we also have these local actors which share local affinity with the WebSockets belonging to each user. So the source of truth state that we actually have on the back end, we're keeping it really simple. We have this connected stroke object, which has a stroke ID, it has a set of points, it has a color, and it has a stroke width. And by the way, I'm using things like value objects here in order to make sure I can't do something dumb like have a 0 width stroke, which would mean it can't get rendered. So I'm basically using some stuff like that here. Connected strokes are the unit of work that the Blazor UI recognizes, and it's also how we think in terms of the total size of the drawing inside our system as well. And then we have our snapshot. This represents what the on-screen data should look like for every user on every client, this drawing session state right here. So we have an immutable dictionary. This contains all the strokes. We have the set of all the available users. We have a timestamp when we were last updated, and then a little convenience property that lets us know if we're starting with a blank slate. Where basically there's no users and no strokes. So that's what we got there. Now, the primary reason we use records, if you're an experienced Akka.NET user, you already know this. We're going to be transmitting this data as messages, and we want to make sure it's all immutable. So records give us that out of the box. That's why we're using it that way. Next, we have the local state inside our actual paint application here, paint.razor. So we're going to basically have this session ID. This gets passed into us via the Blazor routing system. And then we have a dictionary of strokes, a hash set of users, and the last update and the drawing session ID. Now, a question you might be asking, why do I have this immutable data structure, but then I have like a mutable view model of it? Why not just use the same data structure in both places? And the really simple and important reason for why we do this is that Blazor has a much easier time reasoning about things like partial updates when you're working with mutable data structures. If you're working with immutable ones, it's going to go ahead and try to do a full re-render, which, by the way, it might do a full re-render anyway, depending on how you're updating things, but it's going to basically tax the client harder than it would. So we're using it this way. It's just a lot easier to reason about, here's how things have changed since our last render. So that's one of the reasons why we're going to go ahead and use mutable models here. It's just mechanical sympathy for both the end user and for the actual Blazor rendering system. All right, now let's take a look at the drawing session actor. This is where the source of truth state lives inside our system. So what I'm going to take a look at here is our program.cs. This is where we're actually setting everything up. So we're doing a whole bunch of stuff here. By the way, this is where we set the server-side Blazor. This is going to turn the Blazor hub on. We're going to go ahead and also enable SignalR, the JSON protocol, and response compression. These are things I found that usually you need to add. Working with Blazor there. Your mileage may vary though. And let's see, where do I actually add Akka.NET? Here we go. I have this little configure Akka method right here. And this is going to dive into a custom extension method that I wrote that is going to turn on Akka.remote, Akka.cluster. It's going to register a custom serializer. We're going to use Akka.persistence.sql, and then we're going to register our cluster singleton, our drawing session actor, and our local actors here. Let's take a look at the drawing session actor. This is going to go ahead and basically use Akka.cluster sharding. We're going to call this the drawing session shard region. We're going to use DI to start this actor because I believe it takes a dependency on a couple of external services. And we're going to basically just pass in our message extractor and some basic shard options. All right, let's take a look at this. Let's see, let me scroll down to the constructor. Yeah, I guess the only thing this actor actually requires is we have a publisher actor that does some of the D-data synchronization for being able to indicate which drawing sessions are active and how many people are in it. So that's the one thing we're injecting into this actor here. Otherwise, we're going to pass in the session ID. We're going to new up our drawing session state, that immutable object we're looking at earlier. And otherwise, if you followed a couple of my webinars, you know I have this pattern I like to use. If I take a look at our, let's see, drawings. Let's see, drawing session actor. Let's take a look at our commands. Oh yeah, sorry, I guess this is in my entities folder. Yep, here we go. I have my normal structure I like to engage in. Let me go ahead and close other tabs for a second here, where we have drawing session commands, drawing session events, drawing session queries. This is kind of my formula I like to use when working with messages. Queries are messages solely for basically retrieving data. They don't actually affect business state in any way, so there's no side effects. Commands are inputs designed to produce effects. Events are the effects being produced. So that's basically a really simple effect system. Most of these records are very simple, like stroke added, for instance. We have the drawing session ID and then the content of the stroke. All right, fair enough. That's all pretty straightforward. If I receive a drawing session command, I'm going to go ahead and try to call this extension method where I'm going to process it. I'm going to check to see if this stroke already exists. If it does, we can debounce it. So I'll go ahead and basically tell the user we're not going to add it. Otherwise, if we are going to add it, I'm going to go ahead and return a new stroke added event. We will persist that and then transmit it back to all of our subscribers, etc. Otherwise, we also have commands like remove stroke, clear all strokes, add user, remove user. You get the idea. If I go back to my drawing session actor, what I'm going to do here is I'm going to persist all of these events. And then after the event's done getting persisted, I'm going to publish them to all of my subscribers. And these subscribers are the little local session actors that are running on each instance of our Blazor server. So this actor's design is actually very simple. We're not using distributed pub sub or anything complicated. It's basically just akka.persistence handling all of it behind the scenes. The most important thing we do is make sure that we just really quickly process commands, turn them into events, and then stream each of the events to subscribers as soon as we finish persisting them. That helps guarantee that the view state the user has on screen is fully synchronized with what's stored in the database. In the event that we need to reboot this actor, in the event of, let's say, a deployment or a shard rebalancing, it helps ensure that we're fully consistent everywhere. Now, let's talk a little bit more about some of the interesting problems that happen with client sync. So I've already kind of walked through this here, that this is how we're integrating Akka.net with Blazor. This is just using Akka hosting. Akka hosting makes everything a lot easier for integrating Akka.net with anything else in the .NET ecosystem. You should, if you haven't already started using it, you definitely should. One of the things that we're going to do here is we're going to start up our local drawing session actors, and we're using kind of a convenience actor I created called a generic child per entity parent. Basically what this actor does, and I think I have the source code to this in a gist. I had proposed adding this to Akka.net a while ago, and it basically got vetoed because people were worried that you might get this confused with the shard region, but whatever. But basically what this actor is going to do is create local actors using the same message extractor that sharding does. So we're going to spin up these local drawing session actors every time someone tries to fire up a paint session. So on each server, each instance of a paint session, and there can only be one instance of a paint session per server, is going to get its own unique actor. Once we basically go ahead and we start up this drawing session actor, we're going to receive subscriptions from the local actor, and we death watch that actor. So in the event that one of these servers shuts down, we are going to automatically remove those dead subscribers so we don't try to transmit unhandleable messages that that server is no longer interested in. So this is a good practice to make sure that we don't end up accidentally building up debris inside our system. So we watch the sender after we get the subscribe to the drawing session message, and then we remove it from our set of subscribers in the event that that actor dies. Now for local rendering and publishing, here's where the cool stuff kicks in. We have a section tag in HTML, and what we're going to do in order to stream data back to the server is we're going to subscribe to mouse events: cursor move, cursor down, and cursor up. So every time I move this mouse over this section right here, I'm going to trigger one of these events. And the first thing we're going to do is we're going to go ahead and render this little circle. That circle represents my painting cursor. I'm going to render it wherever the mouse currently is. And for each of the strokes that someone has rendered, we're going to go ahead and render this curve. This curve is a custom SVG data structure that's going to go ahead and take all these data points and try to render it in a consistent stroke together. It should look like the exact same size and color as this circle that we had earlier. So from a local publishing perspective, inside our little paint file, in fact, I'll just pull this code up and dive into that file. Let me go to paint.razor. All right, let me scroll down. Actually, if I go to my, let's see, here it is. Here's my section right here. If I mouse over one of these, let's say cursor move, and I hit F12, this will take me directly to the relevant C# function. What we're going to do here is we're going to update these little properties, this CX and CY. We update these little double properties right here with the current cursor position. And if the left mouse button is down, we're going to generate a new point when this happens. This is going to be responsible for creating one point in a connected stroke. Now, what does this onNext method do? This is going to pass a message to our local actor handle using this local paint protocol to say add point to connected stroke. That's what this is going to do. And we're going to go ahead and include the drawing session ID, the user ID, the current position, the cursor size, and the color. All right, looks pretty cool. Let's go ahead and see what this does behind the scenes. So inside our local drawing session actor, in fact, I guess I should go ahead and pull this up. Yeah, now I'll use my little annotations on here. What we're going to do is this is inside the, I think, pre-start method of the local drawing session actor. We're going to engage in some debouncing, meaning that these mouse events can actually be published pretty fast. You don't want to flood the server with tons of little individual data points that all need to be serialized and persisted. You're better off trying to connect those points into a single stroke together. That way we have a slightly larger data structure, but we have many fewer of them when we do that. That's going to make it easier to render. It's also going to reduce strain on the network and the persistence mechanism as well. So group within Inaka streams, we're going to basically say, give us up to 10 connected points, or as many points as you can collect in 75 milliseconds. We're going to aggregate these points into a single connected stroke. So we're going to go ahead and aggregate them together. And then we're going to ask the drawing session actor. This is our source of truth actor running as a sharded entity somewhere. We're going to ask this actor, can you go ahead and basically combine all these strokes together? And in the event that the result was successful, we're going to go ahead and just not really do anything with it. We're going to wait. And we've got another loop that we're subscribed to that's going to have us basically receive the completed stroke in a minute. But if we have a failure, we'll go ahead and log a warning out to the log. The end user won't see this, but you will as the server operator. Now on the client side, we have our drawing session actor. So we've already seen, actually this is the server side still. We've already seen this code. I kind of showed that a minute ago. This is how we're processing these new drawing session commands and how we're basically persisting these strokes and then delivering those new strokes back to the end user. Well, let's take a look at the local drawing session actor and see how this all actually works. Let me go down to, let's see, local drawing session actor. Here we go. So this actor runs locally. There's one of them per paint session on an individual server. Let me go down to our little pre-start method. This is where we create our little debouncing stream right here. And this is where all the actual important debouncing happens. We basically get a set of these add point to connected stroke events from the client. That's what that onNext method is doing. We're going to group all the strokes together by user ID. So if there's strokes that belong to many different users, all in that same batch, we're going to go ahead and separate them out here. We're going to go ahead and batch those together. And then for each of these different user strokes, we're going to create one connected stroke like this. And that line should be fully connected. I think I have a math error right now that's stopping that from happening. But we're going to go ahead and create the stroke. And we're going to specify the color and the width in accordance with the user's dots here. And then we're going to go ahead and add this to the set of drawing commands that we're going to emit as the output from this little function right here. So we're actually going to emit a batch of basically drawing session commands. And then for each one of these drawing session commands, we're going to process them one at a time. This select async call has a degree of parallelism of 1. This helps us ensure that all of these strokes that this client is processing all basically get processed in their original order. And we have to basically make sure each of these events get processed fully before we move on to the next stroke. This should help us keep our rendering fairly consistent across multiple users all connected on the same server. So this is like the right side. This is us writing out to the server. The more interesting piece is probably us subscribing to the server. We tell the drawing session actor that we want to subscribe to the drawing session, and we create a little timer right here that's going to have us retry connecting to the drawing session every 500 milliseconds. The idea behind this is pretty simple, which is that in the event, let's see if I get a subscribe acknowledged right here. If I get a subscribe acknowledged back from the server, this means that our subscription was successfully published. We're going to set up a death watch inside our local actor with the indicator, remote drawing session actor died. In the event that we get this message, which I think I get a little further down here, we're going to retry connecting to that backend server and receiving those updates again. What we're doing here is we're hardening the local actors that run on each of the servers against a scenario where the server actor gets killed and moved to another node, which can happen when we're doing things like a rebalancing or a deployment. So what's going to end up occurring here is we're not going to miss a beat. We're going to say, okay, in the event that the server actor dies and moves, we'll just go ahead and resubscribe, and we'll pick up messages exactly where we left off before. That way we don't even need to redraw the screen. We'll just go ahead and keep picking up new events on the new incarnation of that actor after it gets rebalanced. So that's exactly what this bit of code is designed to do. It's a retry, reconnect pattern. So that's that. Down here, let's see, where is our drawing? These are our local events here that we feed into the debouncer. Other events, we will send directly to the server-side session actor. And then as I scroll down here, these are the drawing session events. This is what the server sends to us. And we feed this into this little for loop here, where you'll notice we're publishing these events to our own set of client sessions that are right here. Huh, what's going on with this? Well, the trick to making this work, if I go up to our, let's see, initialize async, is we go ahead and we basically get reference to the local drawing session actor. We go ahead and we do some startup tasks down here where I'm going to try to get a handle to our local actor. I'm going to ask it to fetch the current drawing session state. That way we get fully synced on screen. And then the other thing I'm going to do is I'm going to feed in this get drawing channel command along with this drawing session ID right here. And we're going to get a drawing channel response. Huh, what's going on with that? When we receive this get drawing channel command, what we're going to do is very similar to what you saw me do on the home page. We're going to materialize a new Akka stream using the source to actorref right here. And we're going to create a system.threading.channel, this channel sync right here. We're going to attach a cancellation token to this flow right here. If this cancellation token gets invoked, that'll cause the stream to shut down. We're going to add this little watch termination event right here to tell us that this subscriber died, so we can automatically remove it from our set of subscriptions. And we are going to go ahead and basically start running this channel behind the scenes. We're going to store that client session inside our dictionary. We're also going to add death watch in case it dies for some other reason as well. We're going to add that. And we're going to tell the sender this drawing channel response, which includes a reference to the drawing channel and that cancellation token that we use to go ahead and orchestrate the stream shutting down if it gets invoked. We feed this back to the paint session right here, this little event stream task. We're going to basically store that channel reader as a property, and we're going to store that cancellation token as a property inside the startup task. And what we're going to do is first render all of the state that we received from fetching that snapshot. We're going to do that here. We're going to render all the connected users. And then finally, we're going to run this little data pump where I'm going to try to read from that channel. And every time that channel has data available, I am going to call handle event, and then I'm going to call invoke async state has changed right here. Now, I think you could probably just call state has changed without doing that invoke async. This is how I used to have to do it on older versions of Blazor and .NET. I think this method has been hardened, so you may not need to do this anymore, but because I'm not 100% sure on basically whether or not this is always safe, I haven't had a problem with it, just doing it state has changed. But this is kind of like the fully bulletproof way of invoking this in an async context if you want to. But, whoops, didn't mean to do that. But basically, this is going to be what drives our render loop. So the primary thing that's happening kind of behind the scenes, I guess I don't have a diagram of that, is that every time I actually draw a brushstroke on screen, let me go back to my UI real quick. All right, let me go and reload that, join this session. Every time I draw a brushstroke on screen, this is making a round trip from me to the server to the database and back each time. And we're keeping that latency pretty low. Now, if this was too slow for our real users inside the system, there's things we could do to optimize that. A really good example would be calling persist async, or we could do things like increase the degree of parallelism on the select async Akka stream stage we're using for debouncing. We have a lot of tools at our disposal as Akka.NET users to try to performance tune this. But out of the gate, running here on a single instance locally on my computer, the latency is just fine. If we ran into problems in a production system, what I would probably do is maybe relax our consistency requirements, do things like publish the event to all subscribers before they get persisted, have persistence happen out of band with publication. That's probably how I would go about addressing that. And this is where we have the subtle issues section. This is the final section of our presentation. I know I'm about 15 minutes over time here. Sorry about that. But let's go ahead and talk about some of the subtle problems. The biggest problem you're going to run into building a two-way streaming system is dealing with disconnects. Disconnects can happen between the individual user and the local drawing session actor. That can happen when a user closes their tab or navigates away from that page. That's one instance. Another problem can happen where the drawing session actor notices that the local drawing session actor disappears because that server restarts. Or that actor could get killed because it's been idle for too long. The drawing session actor has to deal with that. Likewise, the drawing session actor can get killed and moved as a result of, let's say, a rebalancing. And the local drawing session actor also has to know how to deal with that. So one of the things you need to be very vigilant about while designing this application is enforcing disconnect detection everywhere. Deathwatch is your friend. It is the best tool for being able to do this. The next thing you also want to do is guarantee disposal of connection-specific resources. This is what the iasync disposable interface implementation was for. The last thing you want to do is in places where the server and client need to be connected, you need to reinforce retry reconnect, where ideally the client should always try to reconnect to the server. That's the simplest way to implement that. So that's what you saw me do with the local drawing session actor, for instance. So guarantee that stuff gets killed when you're done using it and be very vigilant about it. And if you can, write unit tests to assert that. This will help solve. If you go into production without doing this, I guarantee you, as soon as you have a decent amount of people using your system, you're going to start noticing like Kubernetes pods getting evicted for high memory use or high CPU use and whatever. It's going to be because there's stuff still running in the background that never got shut down properly. So be very vigilant about this. This is a problem stateless systems do not have. So you need to be mindful of that. Finally, we have, well, actually, I think we've got 2 more slides. Performance. Like I've mentioned a couple times now, debouncing is your friend. Debounce on the client, debounce on the server. Your users will thank you for it. This will help result in a snappier, more performant experience. The other thing you should think about is when you're transmitting events, think in deltas, not in wholes. So when we are transmitting our connected stroke added event, we're only transmitting that new stroke. We're not transmitting an entire new version of the drawing. If we had to transmit a new version the entire time, our IO footprint would get huge and our latency would increase. So this is one of the things you can do with a stateful web application, is you can actually do partial updates where you're only pushing the incremental change, not replacing the entire object all at once. These will both help you significantly from a performance standpoint. Then finally, we have data consistency. In our system, we're routing all of our changes through the source of truth. This helps guarantee consistent ordering, all content is accounted for, and makes persistence easy to do. If we came to the conclusion that we were hedging too much on the side of consistency over availability, we could probably relax some of our data consistency. And for this application, it'd probably be okay. Now, if you're ever in a scenario where your client can get horribly out of sync, the best way to handle this is to follow the Akka.NET error handling philosophy. Nuke it. Basically have the client refresh itself and have it repull all of its state from the source of truth and start over. One other thing you could do is that we aren't totally doing this with Draw Together right now, but this would not be super hard to add. If you want to be able to detect inconsistencies inside your client, the best way to do that is to have the server assign sequence numbers. That way, every single event you receive arrives in an expected order. And when you see events appear out of order, that's when you know you've got a consistency problem. And you could go ahead and have the client nuke itself and resync from the server all over again. That's like the simplest algorithm for trying to detect this. So that's all I've got for you today. Thank you very much for attending. You can find the source code on github.com/petabridge, drawtogether.net. And be sure to go ahead and follow us on YouTube and on Twitter. We're going to be doing some more video content around this sample as I continue to build it out, including things like Aspire integration. So hopefully you'll find that helpful. Now, on that note, I'm going to go ahead and take some questions from the audience. So I guess I'll go ahead and start with, let's see, what do we have here? All right, a couple of questions. Let's see. Dang it, is there a way I can undock this? Oh well. Great content, thanks. We use Akka.NET and Blazor today with impressive performance. However, we have this painful issue that I'm simply unable to sort out when using chunking for sending huge payloads to the UI side. There is a buildup of memory that is not released unless manually running garbage collection. Inspecting the allocations shows that the chunked message with byte strings sticks around. I would love to have a way to undock this. Let me try this again. Yes, there we go. Okay. Basically, it sounds like there might be, so Ariel, to answer your question, sounds like there might be a bug with the way we are handling chunking right now. I am going to go ahead and copy this, and I'm going to Slack it to myself and file a bug report later today. So we will investigate that. Okay. Okay, yep, we'll go ahead and file a bug report on that. Okay, next question. There is so much information packed into this training. Are we going to get a recording session to rewatch the meeting afterwards? Yes, you will. You will get a recording. It takes GoToWebinar usually about an hour to record, to render everything, but you should get one relatively soon. And then from Andreas, awesome presentation. Okay, well, thank you very much, everyone. I hope you appreciate it. So yeah, this recording should go out to everyone who's registered within, let's say, an hour or so. We'll double check that on our end just to make sure. Let's see. Okay, one more question from Mike. Why are you waiting for value task.completed task? Let me take a look at that. I believe this is the wrong application. I believe you're referring to what we're doing inside our, let's see, value task, completed task, our homepage down here. Yes, here we go. I don't remember why we did that, Mike. I think I just forgot to get rid of it because I didn't have cancel async written here originally. I think I was just using cancel, and I refactored this later, so I can actually get rid of that, and it's fine. So that was just a bug. So yeah, I'll go ahead and push a new commit that has that fix in there. All right, now if you have any other questions or comments about anything we've covered today, feel free to ask us in the Akka.NET Discord. I'll be back in there in a few minutes. And yeah, you should get a recording. And if after you've taken a look at the recording, if you have any questions, you can also email me. Just go ahead and reply to the webinar from GoToWebinar, and that should go to training@petabridge.com. If it doesn't, let us know. And you can always email me at aaron@petabridge.com. Thank you very much for your time today, everybody. I really appreciate it. And we will catch you next time. Thank you very much for your time.